Hello everyone, my name is Subin from Mobile Network and Communication Laboratory. Uh, I'm going to introduce the paper named Multi-Armed Bandit-Based Client Scheduling for Federated Running. In this paper, the authors focus on how to solve the client scheduling problems in the Federated Running. And in order to solve efficiently this problem, they use the Multi-Armed Bandit algorithm. Before the explanation of this work, we have to understand about what is the federated running and the client scheduling problem. So at first I'm gonna explain briefly about what is federated running. So in these days, modern mobile devices have access to wealth of data suitably for running models, which in turn can greatly improve the user experience on the device. Such as language models can improve the speech recognition and text entry, and image models can automatically select good photos. However, the rich data is often privacy sensitive and large in quantity or both. These may preclude logging to the data center and training there using conventional approaches. Because of these reasons, in the Google research teams, they advocate an alternative that leaves the training data distributed on the mobile devices and runs a shared model by aggregating local computed updates. And the network operates for a number of running rounds as follows. In each round, the clients that are participated in the federated running download the current ML model from the server and improve it by running from their local data, and then upload its individual model updates to the server via wireless link. And finally, the server then aggregates the local updates to improve the shared model. This decentralized machine learning approach is termed as federated learning. So in the federated learning, there is an important issue to solve. It's a latency. For a number of local models to be trained, they need a lot of running rounds. There is the cycles of the procedures that the client download the current model, and after the local training, they upload this local model update to the server through the AP. When it comes to latency caused by communication rounds, such as hundreds to thousands of communication rounds, remains a bottleneck in the federated running. So if the number of cycles are lesser and the latency decreases with the desired model accuracy, it results in performance of the running could be improved. So it is important to schedule the clients to reduce the training latency in the federated running. This work provides a multi-armed bandit-based framework for online client scheduling in federated running. And this client scheduling should be done without knowing the wireless channel state information and statistically characteristics of the client. In this paper, they consider the environment of that wireless network which composed with a single AP and client. And they propose CS client scheduling algorithm based on the upper confidence bound policy, that is CSUCB for ideal scenarios. The ideal scenario is where local data sets of clients are independent and identically distributed, and where the data sets of clients are balanced. And then to address non-ideal scenarios with non-IID and unbalanced properties of local data set and varying availability of clients, they further propose a CS algorithm based on the UCB policy and virtual queue technique. It is called CS UCB queue. And let's talk about the details of the system model of this work. They assume that one AP with n sub orthogonal radio access channel and k sub clients are linked with this single AP. In generally, the number of channels are lesser than the number of clients, so in the non-IID case, this constraint should be considered. But in the ideal IID case, it doesn't matter to not considering it. Let's read the local data sets of client K, which is WK. It has the SK, so sample point. The objective of this federated running is to minimize the weighted global loss function Gx. Global loss is weighted sum of the local empirical loss of the client K. It is GKX. It is defined as the sum of the loss function of a parameter vector x associated with the sample point W, where WK S prime is the S primes of sample point of the client K. The procedure of FL is defined as follows. In step 1, for each communication round T, the AP chooses a subset ST of the clients. And in the step 2, the AP distributes the weight vector xt of the global model to the selected clients. And after receiving the global model weight, in the step 3, each of the selected clients individually updates the global model by computing the gradients of their local loss function based on their own private data, and then upload the updated gradient to the AP. Finally, step 4, the AP aggregates these updates with the dotted updating formula. All of these procedures for one time of communication round, the total time consumed by client K in round T could be formulated by tau kt. In this formula, tau kdt means distribution time, and tau kut means update time, and tau klut means the local update time. And tau max is the maximal interval of each communication round, so it is used to avoid the endless wait caused by the possible stragglers. And let's take a closer look at the ideal scenario first. In this paper, they try to minimize the time cost of FL training process. Therefore, the formula appears as below. The tau st is the time taken by the slowest client at the particular round. The eta value is binary, so eta equals 1 if not reached to tau max, and eta equals 0 if it reached to tau max. And they reconstructed the formula for maximizing the cumulative reward by defining a notation associated with real reward values as RKT. As shown in the lower right corner, that is obtained from the interaction with mobile node. And they define the sigma pi 1, it can be defined as optimal superram minus the mean of this reward as cumulative regret. And they reformulate the algorithm to minimize this sigma pi 1 for maximizing the cumulative reward. To solve this formulated problem, they use an algorithm called CSUGB, the client scheduling UGB algorithm. So at first, lines 1 to 8 are about the initial setting. In this initial setting, it is the process to make sure each arm is played at least one time. The 7th line shows the notation YT and GT, where YKT refers to the sample means of the value of the reward wizard at arm K, and GKT is an expression of how many times arm K was operated until the round T finished. Through this process, once you finish the initial setup, you can go to the main loop from line 9. For each round T, the values YT and GT are updated. The updates are for selecting the optimal arm, it is superarm ST. In this ST expression, the preceding term is exploitation, and the latter term is exploration. On the other hand, non-ideal scenarios consider more realistic situations. Users believe that per channel condition, or depletion of computing power can make it unavailable during the running process. Therefore, we define a new set called AT. This is collection of available clients. Then the superarm ST will be extracted from the client in the AT. And information related to this availability constraint will continue in the following contents. Also, in non-ideal scenario, it is assumed that the local data sets are non-IID and unbalanced. In this scenario, they consider the clients with larger local data set which has a larger size and whose distribution is more similar to the global distribution plays a more important role. And the corresponding clients should participate in more communication round, so they set the selecting rate to be more than a certain percentage with a fairness constraint called CK. However, because it is a non-IID case, we don't know which local data set is actually close to the global distribution value. So they are only considering the favorable clients with larger data set. I will continue to explain the consent related to the fairness condition. During the FL process, some clients could be unavailable temporarily due to the full channel conditions or exhausted computing power. So they define a binary variable AKT, and if client K is available in the round T, then AKT is 1. Otherwise, AKT equals 0. And they also define how to reveal the AT. That is, as the set of the available clients in the round T, where PKT is the power set of K. For simplicity, it is assumed that the set of available clients is IID over time, and the corresponding distribution of the available clients PAE is unknown in advance. However, AT is revealed to the AP at beginning of each round T. Note that in the considered network, the number of clients is much larger than that of the available channel. Thus, the AP has to choose a subset ST from the available clients. And for the fairness constraint, it is introduced to tell each client that how many communication rounds they should be participate. A binary variable BKT is defined as an indicator. So if BKT equals 1, it is indicating that client K is selected in the round T, and otherwise BKT equals 0. Then the fairness constraint is formulated as below. Since the distribution of the local data set is usually unknown, they use the size of the local data set as a metric to roughly describe the importance and set the fairness constraint. The fairness constraint value of the other clients are set as CK. If there exists a policy that can find the time sequence to satisfy the fairness constraint, then the constraint vector C is said to be feasible, otherwise infeasible. So in conclusion, they mentioned on the slide above, in non-ideal scenario, the algorithm 1 in the ideal scenario should have additional fairness constraint. With that in mind, we'll talk about CS-UCPQ algorithm that can solve the problem in a non-ideal scenario. In the non-ideal case, the objective is to maximize the top expression. In this expression, when E is selected set, the P hat AE is the set of selected clients, and QSE is the vector probability distribution, and MUS means normalized level for superarm S. This expression can be reformulated as a problem that minimizes the value called sigma 2. This reformulation procedure is similar to the ideal case. So now let's look at the CS-UCPQ, an algorithm used in the non-ideal situation. It is a similar process to CS-UCP that we've seen before. But first of all, the initialization process has been reduced, and most importantly, to deal with the fairness constraint, we have a virtual queue called DK. This DK tells you the queue length at the beginning of round T. The initial value of D is 0, and if K is selected for round T-1, the queue length decrease by 1 and increase by CK for each round again. This ratio of DK to YKT can be adjusted quickly to super RMST with the weighting factor beta. In this slide, I will talk about the simulation scenarios and the performance of these algorithms. So first of all, in the ideal scenario, they set up 20 clients and 5 channels. Dataset is well mixed and distributed equally to the clients, and they compare the results with random scheduling and round robin as the baseline algorithms. So as you can see from the graph, the proposed UGB algorithm achieves better performance than 2 other baseline algorithms after 20 rounds, and the performance gap increases as the number of communication rounds increases. This is because the proposed CS-UGB algorithm keeps running the statistical information of each client in the execution process and leverage a trade-off between the exploitation of learned knowledge and the exploration of more potential actions. It is also observed that the proposed CS-UGB algorithm has less failed clients, which suggests that in a given time interval, more clients can get involved in the learning process for more communication rounds. Next is the non-ideal scenario. Here we set up 3 clients and 2 channels. Fairness constraint vector is set as C equals C1, C2, C3. That is 0.6, 0.5, 0.4. And the sample vector is 1500 and 1500. And here we have modified CS-UGB algorithms that consider only availability constraints as a comparison group. Without the limitation of fairness, the modified CS-UGB algorithm tends to choose the first clients to participate in the FL process. So this can achieve the smallest performance gap, which is even negative. In addition, different beta values are considered, and these beta values makes the proposed CS-UGB Q algorithm meets the fairness constraint. The proposed CS-UGB Q algorithm with a smaller beta value is more attractive as it achieves a better performance while satisfying the fairness constraint. Next is about the convergence performance. If you look at the ideal scenarios result on the left, you can see that there is a little difference from the comparison group because the local data set is IID. In this case, the average number of clients participating in each round is about the same. On the other hand, in the non-ideal scenario, the client in CS-UGB Q algorithm participated in more round than comparison group. It is resulting in better convergence performance. Finally, in conclusion, this work was aiming to minimize the time consumption of FL training, and this work considered the CS problem in both the ideal scenario and non-ideal scenarios. For the ideal scenarios, they proposed the CS-UGB algorithm and also derived an upper bound of its performance regret. The upper bound suggests that the performance regret of the proposed CS-UGB algorithm grows in a logarithmic way over communication rounds. However, the local datasets of clients are non-IID and unbalanced, and availability of clients is dynamic in the non-ideal scenario. Thus, the authors introduced the fairness constraint to ensure each client could participate in a certain proportion of the communication round during the training process. They further proposed the CS-UCB-Q algorithm based on the UCB policy and virtual queue technique. And they provided a upper bound which shows that the performance regret of the proposed CS-UCB algorithm has a sublinear growth over communication rounds. When beta and T satisfy the condition, simulation results validate the efficiency of the proposed CS-UCB and CS-UCB-Q algorithms, and also reveals a trade-off between the performance regret, the speed of convergence to a point where the fairness constraint is satisfied. This is all of my presentation. Thank you for listening to my presentation today. Thank you.